So we're going to start talking about how we simplify and how we deal with what we call trigonometric identities. Now the good news is that the algebra of trig is identical to the algebra of real numbers. So if we had 2x plus 3x is 5x, which we know is true, we could have 2 sine theta plus 3 sine theta is 5 sine theta. It works exactly the same way. So that's the good news. There's a couple identities or properties that we need to use when we're dealing with these trig problems. One is called the quotient identity, where tan theta equals sine theta over cos theta. So you could try this on your calculator. If you went, you could pick any angle, say tan 30, and then you could put in on your calculator sine 30 over cos 30. And if you tried this fraction, it got the answer, and then if you tried tan 30, got the answer, they would be equal. They would be the same thing. So this is one property we use. Another property, whoops, sorry, too fast. Another property is called the Pythagorean identity, which is basically a Pythagorean theorem in terms of trig. We know this kind of makes sense. We go back to the unit circle, and we talked about how this was the cos of this, the length of the side was the cos, the length of this side was the sine. We know it's a right triangle. We know Pythagorean theorem. We know this side squared plus that side squared is 1 squared. So that's where that's coming from. And we have these reciprocal identities. Since we know that sine reciprocal is cosecant, and then secant and cotangent. So we can relate these things together as well. There's a couple other formulas called the double angle formulas. We have sine 2x and cosine 2x. So sine 2x is really just one that we deal with. And for cos 2x, there's 3 different versions. There's this one, and this one. Now, if we were in the class, all these identities are up on the side wall. You've probably seen them, and they're posted, and you can use them. For us, obviously, for your assignments, you can have these identities out, and you can use them. So don't worry about having to memorize this stuff. It's all going to be given to you. Even the same for next year. Everything, these identities will be given to you, and you can use them when we write things. So we've seen the Pythagorean, we've seen that one, and we can rearrange these, of course. Okay, so let's try a quick example of simplifying. So what are we really talking about here? When we're talking about simplifying, we're really, and this is where it gets a little weird because, I could say, 1 plus 1 equals 2, we agree. Or I could say, 2 plus 0 equals 2. Or I could say 3 minus 1 equals 2. There's sort of all these different versions of the same thing. These are all exactly the same. This is what's going to happen with these trig identities. We're going to have a trigonometric statement, and it's going to look a little confusing, but we're going to try to break it down in using our properties to make it an easier statement. So for example, I could have 2 plus 3 is 5, which is true. Or I could write that as 1 plus 1 plus 1 plus 1 plus 1 equals 5. Well, these are both true, but I think we agree that this one's probably a little unnecessary. It's probably a little too complicated. It's a little too busy. We could simplify this, 1 plus 1 plus 1 plus 1, obviously into 2 plus 3, or even simpler into, whatever, 5 plus 0, or right even down to 5. So the idea with these trig identities is we're going to have a statement that's unnecessarily complex, and we're going to try to use some properties to rewrite them in a simpler form. That's part of the idea of these. So for example, here we have 2 take away 2 sine squared theta. The properties of algebra hold true. I can do some common factoring, so 2 is obviously a common factor in both of these. So I can pull a common factor of 2 up front. And then I know from the Pythagorean identity, I know that if I had sine squared theta plus cos squared theta equals 1. Well, here I have 1 minus sine squared theta, 1 minus sine squared theta. Well, if I can subtract, I can go minus sine squared theta here and minus sine squared theta here, draw my line. Sine squared theta minus sine squared theta is 0. That leaves me with cos squared theta equals 1 minus sine squared theta. So this 1 minus sine squared theta can be actually, here it is here, 1 minus sine squared theta. That can actually be rewritten as simply, as a simpler form, cos squared theta. It's like this complicated 1 plus 1 plus 1 plus 1 plus 1 can be rewritten in a simpler form, 5. So this is what's happening. So this 1 minus sine squared theta is a little bit simpler, I guess, as cos squared theta. And then we can just draw the brackets. So this is exactly the same. So this, when we're saying we're simplifying, this expression and that expression are the same. If you picked an angle for theta, you could pick whatever. You could pick whatever, 17 degrees. You could plug it in there, you could plug it in there, you get the same answer. It's just that this is a better form. This is a simpler form than this. Just like we write 5 as this. We don't write 5 as a whole bunch of sums of 1. Another idea here, cos squared theta sine theta plus sine cubed. We can do some common factoring again. Okay, sine theta is a common factor. There's a sine theta here. We can pull one out here. So I pull a sine theta out front. That leaves me with this inside the bracket. And this inside the bracket is the Pythagorean identity. Cos squared theta plus sine squared theta is equal to 1, which is sine theta. So we really see what's happening here. We have this expression and this expression are the same. They're equal, but obviously this is way simpler. This is way easier to see and understand than this expression here. So that's what we're trying to do. We're trying to rewrite and simplify these things in an easier form. We have cos theta minus sine theta is squared. This is an expansion of FOIL. Just like if we have, a minus b squared, okay, it's a minus b times a minus b. We have to write out both terms. So I have to write this out, and then I have to FOIL to work my way through it. First, outside, inside, last, which will give me this. And then what I see is I can move these terms around, the cos squared theta and the sine squared theta. I can write them side by side. We do that all the time, right? If you have 4 plus x plus 2, right, you're allowed to put the 4 and the 2 together, 6 plus s, right? We collect like terms all the time. So cos squared theta plus sine squared theta is obviously 1. Take away 2 cos theta sine theta. Now we can also factor trig expressions like we do with polynomials, like difference of squares. Okay, remember difference of squares. Same thing with trig. Remember factoring. Find two numbers that add to the middle, multiply to the last. Okay, we've done lots of those. So here we had this one we used FOIL. Let's try this one. So we're going to factor this. Tan squared theta, take away 3 tan theta plus 2. That looks pretty different for us. But if I were to rewrite this, if I rewrote tan theta as x, and I wrote it as x squared minus 3x plus 2, we say this. This looks much more familiar to us. This is just a trinomial that we can factor. This is a trinomial we can factor, but it's a little bit hard to see because the tan is floating through there. So if I just do a quick little substitution, I picked x. You can pick y or a or whatever. I just picked x. This is much easier for us to see. We then say, okay, I need two numbers that add to -3 and multiply to 2. Okay, obviously -1 and -2, that's just simple factoring. And then I put my tan back in, and that's my final answer. That's where I would stop as factored. You can skip this part. If you just want to factor it, right, leaving the tans in and jump all the way down, that's totally fine. Just sometimes it's a little bit easier to put to see it with an x. Okay, we have a fraction here. Okay, I'm going to work on the bottom here. Okay, I'm going to difference of squares. The bottom is this squared minus this squared. That's a difference of squares. Again, that comes from our factoring. And then we see I have the same thing on the top, same thing on the bottom. I can divide out and divide into 1, and I'm left with this fraction. Now we can also use trig identities to prove trig equations true. So to show that the left side of something equals the right side of something. So our strategy for this can be a little bit confusing. So we're going to operate algebraically on one side at a time. So we're going to have a left side and a right side. You just want to pick one side to start on. Then we're going to rewrite everything in terms of sine and cos. Then we're going to factor and reduce expressions. And then we can use substitution of other kinds of identities as we need. And then simplify. So this strategy is important for us to get through those trig identities. So for example, prove the following true. So sine theta equals tan theta cos theta. Again, if you picked 17 degrees and you plugged it in everywhere for theta, you would show it is true for that angle. But we have to show it's true for everything. So here's our strategy. I have a left side, I have a right side, I have sine theta at my left, I have sine theta cos theta on the right. Sorry, I have cos theta on the right. I'm going to replace tan theta with sine over cos. That's what this is here. That's my replacement. Tan theta is sine over cos. And when I do that, I have a cosine in the bottom, a cosine in the top. They're going to divide out. And that leaves me with sine theta equals sine theta, which shows the left side equals the right side. Okay, so that's a simple version of these kinds of proofs. How about this one here? Prove 1 minus sine squared theta is sine squared theta over tan theta. So I have my left side, I have my right side. On my right-hand side, on the left-hand side, I've seen this 1 minus sine squared theta. That kicks into cos squared theta, okay, from the Pythagorean identity. We saw that before. And I'm going to replace tan squared theta with sine squared theta over cos squared theta. So here, this sine squared theta is that sine squared theta there. And then this tan theta becomes this. Becomes the sine squared theta over cos, because tan is sine over cos. And we say to ourselves, well, how do we divide by a fraction? When we divide by a fraction, we flip it and we multiply. So I'm going to flip this fraction and we're going to multiply. And when I do that, of course, the sine squared is going to divide out, and I'm left with the cos squared theta, which shows the left side equals the right side. So for these to work, and the questions, remember, they're going to be set up, okay? The questions are going to be set up so they work, okay? They're going to have a certain structure, so when you do some substitution, some algebra, they will break down, and the left side will equal the right side. This one here, secant theta cos theta plus secant theta sine theta, 1 plus tan theta. So the left side, the left side is pretty big, so I'm just going to go right into the left side. I'm going to replace secant with 1 over cos, and secant with 1 over cos. Okay. These divide out, of course. I have a 1, and then left here was sine theta over cos theta, which is 1 over tan theta, which is the right-hand side. So sometimes with these larger sides, you can just pick that, and don't worry about the table. You don't worry about fitting the table in. You can just work through the one side and see that eventually when you stop, it'll hit the right-hand side. Okay, that's it. So we'll try some questions on 273.